Welcome to this lecture on some slightly more advanced DEA. In this lecture, I'm first going to remind you the basic idea of estimating a DEA technology, and then I'm going to introduce an extra efficiency notion, namely that of super efficiency. And then I'm going to also go back to some of the notions we started with and show how to actually implement them in the DEA program. And having done that, there'll be some exercises where you can try these different things, directional distance and stuff like that. And then the next sort of section of the presentation will cover an alternative way to look at the DEA model, namely the ratio formulation. And I will also cover the possibilities of including not full, but partial price information, or you can also say preference information into the evaluations, and in this way get more refined evaluations than pure technical efficiency. And at the end, I will discuss some more theoretical stuff about the classes of functions from which we try to estimate when we use DEA, looking at it slightly more like a statistical problem. And I will also cover some more theoretical stuff about the relationships between technology, the distance functions, and the cost functions. And I'll show that these are just different ways of describing the same thing, basically. So you have a choice whether you want to describe technology sort of technically, the way we've done it as a set, or whether you want to define it via a function, the distance function, or via another function, the cost function. So let's dig in and see what it all looks like. So some slightly more advanced DEA. Let's see. So as before, I want to remind you that what we're going to talk about here, namely the estimation of the technology and the measurement of efficiency relative to the technology, that's really just a small part of a real benchmarking study. But it's sort of the more technical part, and it's the more academic part of it. So we're going to focus on that in this presentation again. The outline of the presentation is I'm going to first remind you about how we estimate the technology, and then I'm going to show you how we can implement some of the efficiency concepts we talked about already, namely efficiency when you have non-discretionary variables, and also the directional efficiency measures, but I'm also going to introduce one new efficiency concept, namely that of super efficiency, and I'll explain why this is relevant. Having done that, we'll do some exercises where you actually try to implement these things in R, and also if you have time in interactive benchmarking. And then we move to the second section where we're going to discuss ratio and game interpretation of the DEA program. So a rather different way to interpret the program. Instead of thinking of proportional reductions, there's some alternative ways that you can think of the efficiency program that can be very useful in some context. And we're also going to discuss how you can include partial price information or some preference information into the analysis, so as to get more refined measures of efficiency. And finally, we're going to cover two somewhat more theoretical parts, the DEA cost and production functions, the nature of those from an abstract point of view. And then we're also going to discuss these dual relationships between technology, cost functions, and distance functions. Technology estimation, I just want to remind you that this whole idea of DEA, so the general idea is that you estimate using the minimal explanation principle. So you collect some data, so you have your data points, which are the input and output vectors of some firms I. And now we find the smallest subset of input-output space that contains these observations, and at the same time satisfy certain regularity assumptions, mild regularity assumptions. The fact that we find the smallest subset means that we makes an inner approximation of the true technology. And that also means that we make cautious evaluations, because the improvement potentials we can find when we compare to a subset of the technology is of course smaller than the possibilities we can find if we have the true technology, which is larger than the estimated technology. Okay, another way to express that is to say that we create conservative estimates of the improvement potentials. The different DEA models vary basically by the additional assumptions they make. They're all based on this minimal estimation principle, but they vary in terms of the additional assumptions they impose on the technology. And we already talked about that. We saw, for example, that the variable return to scale DEA model assumes free disposability and convexity, and basically nothing else. And we can describe the technology like down here, where this gamma, capital gamma set is defined by these extra constraints over here. So we have variable return to scale, the sum of the lambdas, which are these weights we put in the different firms, they have to sum to 1, okay? And if we had constant return to scale, there's basically no assumptions about these lambdas, except that they have to be positive. And similarly with the other ones, we talked about that in the initial presentation of DEA. So these are the basic assumptions, and this is the technology we're going to measure in relation to in this presentation. Now, we talked a lot about different ways to measure efficiency already in the efficiency measures presentation. And we also talked a little bit about how to implement feral efficiency in the DEA program. What I want to do now is I want to introduce one new efficiency concept, namely that of super efficiency. The idea of super efficiency is that when you evaluate me, for example, my data cannot be part of the data that spans the technology. So you basically leave out the evaluated unit from spanning the technology. It's very simple to do in reality, because it just means that when you have these sums of the lambda xi's that you compare to, and the sums of the lambda yi's that you compare to, then normally I would be one of those that I'm being compared to. But if you want to do super efficiency, you just remove one column from this program. And the way we write it is like here. So we say that the feral input super efficiency for firm number I is the evaluation of my firm against the technology that is estimated without me. So this is sort of the game notation you often use, that if you write like minus I, it means everyone but firm number I. And this we can also use as you do the same, of course, on the output side, then you get output feral efficiency in the super version here. Why is this relevant to try to measure efficiency like that instead? Well, one of the original proposal by Anderson and Peterson was actually that they wanted to differentiate among the fully efficient firms. When you do a DEA analysis, there will be a lot of firms sitting on the frontier, and maybe some of them could still be considered to be more efficient than others, or more productive than other firms are. And in this way, you actually get a measure of, as I'll show you in a split second, you get a measure of how much a firm contributes to pushing the frontier out. So you are rewarded in this measure by contributing to pushing the frontier out. And this is actually extremely crucial if you think about incentives, because otherwise, if you're already sitting on the frontier, you have absolutely no incentives to improve. And actually, if you're sitting on the frontier, in most cases, you could actually introduce a little bit of slack and still be on the frontier. And so it gives really bad incentives to rely on normal efficiency measures unless there are some other factors going in, some uncertainty, you don't really know what the others are doing and stuff like that. But from assuming perfect information, it is necessary to use super efficiency if you want to provide good incentives. I also wanted to mention that super efficiency is just an extension of the normal efficiency concept. So if you know super efficiency, you can reconstruct normal efficiency, because the normal efficiency is just the super efficiency as long as that is less than 1, and otherwise it is 1. So when super efficiency is larger than 1, then we just give the normal efficiency, we'll just say when it's 1. Okay? So it's a more refined measure. There's a slight problem with that, and that is in some cases it might not exist, because I might actually be defining the frontier in this area where I am. Maybe I'm alone in this area. I have an input-output mix which is very special, so there's no one I can really be compared to. Then you'll normally just get an efficiency score of 1 because you define the frontier. But if you are not allowed to help define the frontier, then it might not be possible to, if you want to do a proportional reduction, you might not meet the frontier. If you want to do a proportional expansion, you might not meet the frontier. And in that case, you basically cannot calculate super efficiency, or we would say that you get a super efficiency of infinity or minus infinity. Okay. So let me just give you the intuition, graphical expression of what is going on here. So let's assume that you have some firms F, G, H, and J and I. So they are the real firms. This red one is not a real firm. So I'm looking at this firm. This is in input space, input 1, input 2. I'm looking at this firm here, K, and you see that it will get a Farrell efficiency, input efficiency of 1, because you cannot reduce your input proportionally, because you're already sitting on the frontier. Okay, but the point is that even if I were to increase my use of resources with, say, 5%, so I get to this area here, then I will still span the frontier and I will still get an efficiency score of 1. I could actually do that all the way up to this level here. So super efficiency measures how much could I have increased my inputs before becoming inefficient. The Farrell input super efficiency measures how much could I have increased my input before becoming inefficient. And on the output side, it measures how much could I have reduced my services provided and still look perfectly efficient. Okay, so if we look at the input side as here, we can see that G could have increased the input consumption by moving out to the new point G star. Sorry. So let's assume that that is sort of a 20% expansion. That is G star is equal to 1.2 times G. Then we say that the super efficiency of this measure is 1.2. So large super efficiency on the input side suggests that you could expand your consumption of inputs without looking inefficient. A small super efficiency on the output side means that I could have reduced my services and still I would look efficient. Okay. And with this picture, I just want to illustrate why this is important. Okay, the first thing you can note is that now you can say that this guy here, he has an efficiency of 1.2. You can now do the same for this guy here. Then he'll be compared to H, G, and it'll go up like this. And maybe he could expand his inputs with 1.4. And so you can, in this way, firms that would normally just get an efficiency score of 1, they will now get different efficiency scores. This one may get 1.2, this might get 1.4, and so on. So you can sort of differentiate among the firms that are fully efficient in the normal Farrell sense. Okay, so that was the initial purpose of introducing super efficiency. That it was to differentiate, get a more detailed description about performance on the frontier. From the incentive point of view, this picture will illustrate why it's relevant. Assume that I have technology. If I'm supplying a lot of my full effort, you can produce out of this frontier here. And I have now two firms, A and B. If we do a DEA analysis, we're going to estimate this. We don't know this technology in reality. So instead, we estimate it as a DEA frontier. So we move from here to here to here to here. Okay. All of these firms are assumed to use the same inputs. So we get this level here. So they're both getting a score of 1. Okay, and maybe you get a reward when you have a score of 1. So now you get a reward as firm number A. Now firm number A would say that, okay, I get a reward because I'm fully efficient, but what would have happened if I more than halved my output and moved from A down to C? I will still become fully efficient in the DEA's model, and I will still get my reward, but I only had to work half as hard. So of course your incentives are not inspiring you to actually move out there. And assume that A went down to C. Now what could B do? Well, he gets an efficiency score 1 here, but what happened if he moved from B to D? Well, he would now also get an efficiency score of 1. So he would move down to D, but once he has moved down to D, then actually C would move down to a level here, and so on. So actually you can see from this small illustration that if you only reward people for their normal feral efficiency, then you'll end up in a situation where nobody really does anything. And actually in one of my earlier papers on this, I showed that the only Nash equilibrium you can sustain with usual feral efficiencies is an equilibrium where everyone is doing the least effort, providing the least effort. Okay, so super efficiency is a useful concept, and in the R program we have it's actually very simple to do, but in the R program we have one called DEA Super also, so that to make it even more easy. Having covered that, I want to look at two of the notions of efficiency that we actually already talked about. I just want to show you how easy it is to actually implement it. And again, it is implemented in the R package, in the benchmarking package written in R, and you can also do it in exactly benchmarking. But assume that you have a context where you have two types of inputs, variable input and fixed input, or discretionary input and non-discretionary input. And then you have a given output, and you want to evaluate how efficient this production plan is in this technology G. And we talked about that the proper way to do that was to say that, okay, since I cannot control my fixed input, the non-discretionary input, I should only try to proportionally reduce my variable input or my discretionary inputs. So that was what we talked about when we discussed it in the presentation on performance measures. Now that is really, really easy to implement in DEA, because you just do like a normal input efficiency DEA program. The only difference is that you have this E factor, this proportional reduction factor, is not going to be imposed on all the inputs. So you remember you have a lot of input rows. You're only going to impose it on those input rows that are controllable or that are variable. So I've split up my input constraints here in 2. The usual input constraints are split in 2, and I'm only applying this reduction factor on some of them. The rest stays constant. And then I have my usual output constraints. So that's the only change you need to do in the linear programming. So it's very, very easy. Another notion we talked about was this idea of directional distance. So you can imagine a situation where you want to reduce the inputs, but you're not so sure you want to reduce them proportionally. Maybe certain inputs you would prefer to have reduced faster than some other inputs. So you could imagine a situation, you could use the excess function for that, or the directional distance function for that, where you try to maximize this E factor that you multiply on the direction in which you would like to move. And then you say that, okay, I want to find the largest one such that the inputs that are left, that is the original input, minus this E times the direction in which I would like to move, is able to produce Y. Okay, so here I have one input, one output illustration. I have my observation here. This arrow indicates the direction in which I would like to move. And then this term I have here is this x minus e dx here. In this picture, there's an extra indication that it's on the input side. It's not up here, illustrated up here. So I just use dx down here and just d there, but that's minusing. So this x star is when you have solved it and you found the maximum reduction, you end up in this point, the circled dot here. Okay, how do you do that in a mathematical program? Well, you want to maximize your E. You want to find, as always, the weights you can impose on the frontier, on the firm, so as to construct the frontier. And what I just need to make sure is that this input I have left, which is this one here, is more than what is needed on the frontier. And the unit on the frontier is producing at least what I'm asking for here, the Y0, okay? So so we have zeros here and we don't have it up here, but you see the idea, okay? The biggest, so that's kind of an interesting notion, but the biggest problem with application of this is that how do you choose this direction? And in the literature, there's been there's always some complaining about if you go in a different direction, people will ask, oh yeah, but why did you go in that direction? So you normally need a really good story for that. Something about some things that are more easier to change, or it's more discretionary than other things are, or that it's more expensive, or something like that. You need to come up with a good reason why you should use this direction D. One of the argument, as a contribution to this whole discussion, I did a paper some years ago with Jens Hågaard, where we discussed one way of picking this direction in a proper way, and I just want to illustrate what that is. So assume that you have some input 1, input 2, you have some firms, A, B, and C, and I want to evaluate this firm number B, and I want to do a direction, but it is not necessarily going to be proportional, it's not necessarily going to go directly down to the 0 point. Instead, the idea is that you project this point on the frontier in this direction and in this direction, and that kind of gives you a point down here and a point here, which so that the conditional ideal would be like this. Okay, let's think of an example. Okay, so you have a production process, and you have a hospital, for example, and you have nurses and doctors, and so you ask, I have an inefficient hospital here. How many doctors could I have removed if the nurse level stays constant? So what are the saving potentials in the doctors alone? That is this line down here. Okay, what is the saving potentials on the nurse side if I let the doctor numbers be sticked? So assume, for example, that I'm located in a place where I could save one doctor, or I could save 2 nurses. Then we suggest that that is the proportions in which you should reduce them. You should, whenever you do it, you should get rid of 2 nurses for each doctor you get rid of. Here's more or less 50-50. So, but anyway, this basically means that you're going to move in a direction towards this conditional ideal here. So why did we come up with this? Well, it's based on some bargaining theory, actually some Kalai-Smoldinsky bargaining theory that says that if you have some groups that have to bargain, then the question is, what could they have, what are their potentials alone? And what is one group's potential alone? What's another group's potential alone? And then you need to sort of share the combined gains in proportion to what they could have accomplished on their own. Okay, here it's kind of something negative you can accomplish on your own, because this is the reduction of doctors you could do on your own, and this is the reduction of the nurses you can do of your own. But we are sharing this requirement of improvement in proportion to the amount of improvements you could have done on your own. That's the idea of it. So we provide an axiomatic foundation for choosing exactly that direction. And that might help you in some contexts to actually argue which directions to use in a directional distant function approach. Okay, so this was just a brief introduction to some new material, and we'll take questions now. And after that, we will discuss, I'd like you to do an exercise. And I put in an R script here. You can try to do it. What you are going to do is that you're going to do a DEA analysis of some water. You're going to do the normal efficiency, federal efficiency. Then you're going to try to solve exactly the same problem with a directional distance approach, which we handle over here with the DEA feature in DEA. And the purpose is that you should try to understand why you get different results here and here. Although in this case, I'm moving in that direction, the direction of my own input vector. So in principle, I'm moving towards the origin of the coordinate system. I want you to try to calculate also super efficiency. And then I would like you to do more like a directional distance evaluation, and try to understand the results you get out of it. And then you can try to do exactly the same in the interactive benchmarking program. So that will give you a good idea of the concepts that we talked about and how to put them to actual use on real data sets. And here's actually the results you're going to get out. But the question is not so much to get the results out, it's more how to interpret them. But it's useful to get a hands-on feeling for how to get these results out. Okay,